Welcome back to ECE 320A. This is video number 2 in Unit 10. And again, we're dealing with Bode plots, which you're taking your material from Appendix E. Homework number 10 is at the end or due at the end of this unit. And exam number 4 will happen after completing this particular unit, which is Unit 10. What I want to do now in this video is work through the steps for sketching the Bode plot of a first order transfer function. Once you see this for a first order, then hopefully it will start to become somewhat clear why we're doing what we're doing in subsequent videos talking about putting all of these different pieces together. But let's start with a straightforward piece, which is looking at sketching the Bode plot of this standard form transfer function h of s equal to k over tau s plus 1. And I should start by saying that this particular transfer function has been already placed into a standard form. This is our time constant form, which means that we've factored the denominator such that this constant coefficient has been normalized to 1. If that was something else, we factor that something else out and force that coefficient, that constant coefficient, in our linear denominator factor. We just have a s to the 1 power in the denominator. We factor the denominator such that the constant coefficient is 1. Let's look at a quick example of that so that you understand that, oh, well, I can't sketch this because it doesn't look like k over tau s plus 1. Well, given any first order transfer function, you can convert it into that k over tau s plus 1 structure. And to do that, this is now in pole 0 form that we're starting with. This transfer function, capital H of s, is 40 over s plus 5. We factor out that pole. We normalize that constant coefficient in the denominator so that the denominator constant coefficient is 1. So that means that if we factor 5 out of all the terms in the denominator, since we just have a single linear factor, we now have the denominator looking like 5 times the quantity, s over 5 plus 1. That's really all we're doing to find time constant form. We keep 40 up there, but now we can manipulate this so that h of s is now, if we move the 5 from downstairs to the downstairs in the upstairs, if that makes any sense, we now have 40 over 5. And let's go ahead and separate that s over 5 into two pieces and say that we now have 1/5 s plus 1. We haven't done anything different or that magical, but now we have this transfer function that is 8 over 1/5 s plus 1. Well, this is now k over tau s plus 1, where k is equal to 8. That's our DC gain. If we set s equal to 0, our DC gain now is 8. The DC gain is also 8 if we found the value for s equal to 0 there. So we haven't changed the DC gain by transforming it from a pole 0 form into a time constant form. And our time constant tau is 1/5 of a second, or 0.2 seconds, which in this case, after 5 of those time constants, or 5 times 0.2, I shouldn't have maybe picked 5 for my pole location, but now we have a settling time of 1 second. And that's just an example to show you that it's not anything magic that we're assuming. We're not assuming anything dramatic by saying, let's start with learning how to sketch a Bode plot for a standard form transfer function in time constant form of k over tau s plus 1. You give me any first order transfer function and we can convert it into this structure k over tau s plus 1. If that's the case, let's now see how we can sketch this first order transfer function. Let's look at the magnitude of h of s in dB. The magnitude in dB, we take the magnitude of that, we're sketching the Bode plot, which means we're looking at taking s and evaluating s along the imaginary axis, or we're evaluating this transfer function when s is restricted to j omega. So if we're thinking about what we're doing, here is our s-plane. Wherever I ended up with. Now here is our s-plane, and we are actually evaluating along this j omega axis for our transfer function. In our case, we might have a pole here. We are now looking at what the magnitude or the distance is between this point and that point, between this point and another frequency, and we're also looking at these angles as those change as we march up the imaginary axis, and we've talked about this in our frequency response behavior, or evaluating h of j omega graphically. We want to now speed that process up so that we manually don't have to investigate an infinite number of frequencies omega. We can simply do this straight line approximation approach to obtain a nice approximation of our Bode plot magnitude and phase as a function of frequency. The magnitude of our transfer function is then in dB 20 log of the magnitude of h of j omega. In our case, that's 20 log of this particular first order expression, which is k over, and we're saying tau s plus 1, but we've replaced s with j omega, so this is j omega tau plus 1. Using the quotient property of a logarithm, we now have 20 log of the numerator minus 20 log of the magnitude of the denominator. We can also look at the phase. We're going to really be focusing on two different sketches in this Bode plot. So now the phase, or the angle of this transfer function, is the angle of k over j omega tau plus 1. Knowing how the angles of these factors work together, in this case we have all of our numerator factors angles added, and we subtract from that all of our denominator factor angles. In this case, we have one numerator factor, which is k. We take the angle of k. If that's a positive number, that angle is 0. If k happened to be negative, then the angle associated with that would be 180 degrees, and we'll really usually prefer to use minus 180 degrees. Then we subtract the angle of the denominator factor, which this one now, tau is fixed. Our time constant we're leaving constant, obviously, but now omega is being adjusted from some small value, dc, up to an infinite range. We now have seen, hopefully, a couple of, or we can make a couple of observations from just looking at the magnitude and angle of this first order transfer function. In this particular case, for this transfer function, we can identify two different terms, or two different factors. We have a gain term, and we have a linear pole factor term. And what we want to do now is look at the magnitude and phase as a function of frequency for each of these terms, the gain term and the linear pole factor term. So let's look at the gain term first. We now want to sketch, or say, what's the straight line approximation associated with, or straight lines, and in this case we're going to see that k is not a function of frequency, so this is just one value for all omega. No matter what omega you pick, the magnitude associated with this term, this constant term, is 20 times log base 10 of the magnitude of k. If you wanted to think of that, then Now, depending on what you have, if k actually ended up being 10, let me say that k is equal to 10, then 20 times the log of 10, the log of 10 is 1, so that's going to put you at that particular flat line in this plot or sketch of dB versus frequency for a constant value k equal to 10. And the dB now allows us to sketch a wide range of magnitudes over or on a particular small or not large section of our paper. What would correspond to 40 dB? Well, now if we looked at k equal to 100, now we have 20 times the log of 100. The log of 100 is 2, and so now we have 2 times 20, or 40 dB. So you can see then that because we're sketching this in dB, there's the possibility of having a very large value, k, collapsed into a fairly small vertical distance. What's minus 20 dB? Well, if we looked now at k equal to 0.1 or k equal 10 to the minus 1, that's now going to be minus 20 log of 10. And where did that come from? Well, that's just 20 log of 10 to the minus 1. The minus 1 pops out front. We have minus 20 log of 10. Log of 10 is 1, so we have minus 20 dB. I think you can anticipate what would happen for what's the gain value k to give us 0 dB. If we had a k equal to 1, now 20 log of 1, log of 1 is 0, we're right there on the 0 dB line. So depending on what k is, if k is now 5, now we might have log of 5 being 0.7, and we now multiply 0.7 times 20, or we now have 14 for our gain, and we would then sketch that curve if k was equal to whatever I just said, which was 5. So now, depending on what k ends up being, we just draw a line, a flat line, as a function of omega. That's now the gain term, Bode plot, as a function of frequency. How do we sketch the phase of that gain term? Well, now I've already hinted at what this corresponds to. If, in fact, the gain k is non-negative or positive, then the angle of a positive number here in blue, if we look at what is the angle to get us from the origin out to there, you can see that we don't have to look through any angle. That's just flat. That's 0 degrees. Conversely, if we look at the angle between this horizontal positive line and where we need to go when k is negative, then we can either go a positive 180 degrees or a negative 180 degrees. And as I said, let's go ahead and just use the minus 180 degrees because we're usually thinking about delays, and a negative value will give us a delay. So, depending on what k is in terms of its sign, S-I-G-N, then we will either have a phase curve that is here at minus 180 degrees for all frequencies, or if our gain k is positive, then it's not contributing any angle as a function of frequency. And so this is now going to be when k is greater than or equal to 0, and this particular sketch of our phase, this is now the angle of k, is when k is less than 0. That's now all there is to sketching the Bode plot associated with a constant. Let's now look at the linear factor. The linear factor is now tau s plus 1. This is now, in our case, going to be in the denominator, but for starters, let's just look at tau s plus 1 so that this can be generalized to a numerator linear factor or a linear denominator factor. For now, let's just look at tau s plus 1. Again, we're evaluating this when s is a frequency expression or on the imaginary axis, so we're setting s equal to j omega. This now becomes, this linear factor now becomes j omega tau plus 1, and tau is a fixed number. In our earlier example, tau was 1/5 or 0.2. We now want to see what happens to this factor in terms of its magnitude and phase as a function of frequency omega. Suppose we look at 20 log base 10 of the magnitude of j omega tau plus 1. And to do this, let's now look at some extremes. And here I like to invoke your memory of an earlier fable, and let's just think in terms of Goldilocks. And maybe this will allow you to sort of keep this in perspective in terms of it's not that much rocket science. Goldilocks, maybe it's a little bit too cold, maybe a little too hot. What's just right? Well, we're going to be looking at those kinds of extreme conditions. So we may have a low frequency, we might have a high frequency, and we might have a frequency that we would maybe consider just right. And in this case, when we just have the one factor, linear factor, that's a function of frequency, this just right frequency is actually going to be our break frequency, or where the pole is. So now, let's look at some of these extremes. Suppose in this argument of our logarithm, we look at the case where the imaginary component, where omega tau, suppose that coefficient is much less than 1. What does that mean? Well, now in red, when we can see what that translates into for omega. Omega it being much less than 1 over tau, and in our case, remember, tau was 1/5, so 1 over tau is 5. So what happens when omega is much less than 5, 5 being our break frequency? What we are going to consider to being much less is going to be a factor of 10, and in this case, 1/10 of the break frequency. So consider much less being a decade below the break frequency, or a 0.1 times omega sub c. If we now look at what this is, written another way, so we've looked at this expression, omega tau much less than 1, that's really just the imaginary component. When is that much less than the real component? We can solve that, or we can divide both sides through by tau, and we now see that we have this relationship. Well, this relationship is just expanded upon over here. Tau is the pole's time constant, so 1 over tau is just the pole. I hope that's clear. This is now, in fact, this 1 over tau is just omega sub c. So what do we mean? One of the extremes is when omega is much less than omega sub c, and much less, we're saying, is 1/10. So what happens when we approximate j omega tau plus 1 with a frequency omega much less than omega sub c? Or when omega is less than 0.1, 1 over tau. Well, now we have j.1 or less plus 1. And I hope that it's okay, or you're comfortable with saying, oh, that means that really if we have 1 plus j times 0.1 or j times 0.01, something less than j.1, let's just go ahead and approximate that to be equal to 1. That means that if we're looking at 20 times the log base 10 of the magnitude of j omega tau plus 1 under this condition where omega is a decade or more less than the break frequency, then we can approximate this argument of the logarithm by simply 1, so that now we have 20 log base 10 of 1, and the log of 1 base 10 is 0, so that now this factor, this linear factor, a decade before the break is really going to be approximated by a flat line having a value of 0 dB. That's the one extreme. That's the low extreme, thinking Goldilocks. Let's now look at the high extreme. Being consistent, low meant a factor of 10 below omega sub c. High means a factor of 10 greater than the break frequency. So now that's what we want to consider omega being equal to, or larger than, or exceeding. So the high frequencies are a decade beyond the cutoff frequency. And now what happens to this j omega tau plus 1 when we approximate it when omega gets bigger than 10 times omega sub c? Well, now omega being greater than 10 omega sub c says that that's now bigger than 10 over tau, and we're multiplying that by tau. So now we have j10, or j something bigger than 10, plus 1. Well, 10 is much bigger than 1, so we're really going to say, let's then just go ahead and approximate this complex expression as just the imaginary component. So this now becomes j omega tau. Or what does that mean? We now can say 20 log for this high extreme frequency case is now the magnitude base 10 of j omega tau plus 1. That's now 20 log. We're throwing away the constant. It's now the magnitude of j omega tau. And tau, again, is related to the cutoff frequency reciprocally. So tau is 1 over omega sub c. We now can say, oh, we're now equaling 20 log of omega over omega sub c. We now have 20 using this characteristics of logarithms. We can now take the difference of that ratio in logarithmic terms. We now have 20 log of the numerator. This is now, think through what we have. Log of omega is really, in the Bode plot, our independent variable. That's what we're plotting everything with respect to. So in fact, we now have this independent variable, our x, scaled by 20. And what is this piece? Well, this is now just a constant, because omega sub c is fixed. This is now just a constant value. What we want to do is figure out what would happen at sort of this sweet spot, or what happens when these two pieces are actually the same. Again, it's really the difference between 20 log of omega and 20 log of omega sub c. Well, if omega is equal to omega sub c, I hope you can see then that you have 20 log of omega c minus 20 log of omega c. That's going to equal 0. So what happens when we are right at the break frequency? We're right at the sweet spot. And when omega is equal to omega sub c, we have 20 log of j omega tau plus 1. Again, this is at this intermediate point between the low value, Goldilocks, and the high value. So the approximation when omega is much bigger than omega sub c provides us with this relationship, and that now says, oh, using that relationship, if we go all the way back with that approximation, we actually see that it meets up with our low frequency approximation of 0 dB at this sweet spot, or at the just right frequency, which is the break frequency. So we know that we're decreasing for high frequencies because this is a denominator factor, this j omega this j omega tau plus 1 factor. As omega gets bigger, that just makes the whole transfer function get smaller. Then we have the low frequency behavior, which is 0 dB, and we've now found that those approximations actually meet at 0 dB at this sweet spot, or at the break frequency omega equal to omega sub c. So let's now look at that for this particular factor, which was a pole factor. That's why we're now in the basement. The pole factor is now j omega tau plus 1 raised to the minus 1. It's in the denominator. It's in the basement. We then have 20 log of the magnitude of j omega tau plus 1 inverted. Well, that exponent of minus 1 gets placed out front because of the properties of logarithms. We now have minus 20 log of j omega tau plus 1. So now we have this negative slope for denominator factors. If it was in the numerator, that would not be a minus 1, it would be a plus 1, and we would have a positive slope. So if we have factors downstairs in the denominator, those are going to have negative slopes, magnitude. And if we have numerator factors, those are actually going to have positive slopes. So here is our straight line approximation of the linear term. For frequencies less than 1/10 the break frequency, that's right here, we are at 0 dB. For frequencies bigger than a decade beyond the break frequency, here is our break frequency, omega sub c, then a factor of 10 beyond that, let's say that omega sub c was 5. Then 10 omega sub c would be 50. 0.1 omega sub c would be 0.5. We know what those are prior to or on the extremes. We're approximating at a 0 dB for low. We're going down at minus 20 dB per decade because it's a pole factor. We can see then, hopefully, that in between those two approximations, they now meet at the break frequency in our straight line. So now we really just need to know what's happening at low frequencies, what's happening at high frequencies, and making this break occur at the break frequency omega sub c. That's now what we would sketch for our straight line approximation. We would go 0 dB out until the break frequency, and then beyond the break frequency, we would simply say, oh, now we have I told you I couldn't draw a straight line. We now have a slope of minus 20 dB per decade. That's just one factor, and it's going down at 20 dB per decade. And here is just a little bit more explanation of this slope. M is minus 20. That's where that's coming from. Our independent variable x is log of omega. That's what we're sketching all of our Bode plots with respect to, even though we usually just call it frequency. It's actually log of omega, and that allows us to put more frequencies in a condensed linear space. And we have our intercept term of 20 log of omega sub c. That's our b. What's the phase look like? Again, thinking Goldilocks, we have a sweet spot. We have a low, a high, and a sweet spot. Let's look at the low frequency. So for small frequencies, that's a decade below the break frequency, omega sub c. We know how to approximate that. We have 1 plus j 0.1 or less than 0.1, so we'll just approximate that to be 1, and that gives us an angle of 0 degrees. At high frequencies, a decade above omega sub c, now we're throwing away the 1, the constant term, and just keeping j omega tau. The angle of j omega tau relative to the horizontal, positive horizontal line is just 90 degrees. If you wanted to look at this in terms of now we're up here at some j omega tau, hopefully you believe me that that's now this angle, and that angle is 90 degrees. So if we get far enough away from the break frequency, and here far enough away means 10 times the break frequency. We're now a decade beyond the break. We're going to say that anything above that, that particular factor contributes 90 degrees. Anything less than a factor of 10 less than the break frequency, we're going to approximate that as 0 degrees. What do we do? Well, what happens at the sweet spot? The sweet spot is actually at the break frequency when omega is equal to omega sub c. We look at that particular value of omega, we plug in omega equal to omega sub c. Tau, remember, is just 1 over omega sub c. That's our relationship with tau. Remember, we had this s plus 5, and this was now our omega sub c, and we factored that 5 out, and we ended up with s over 5 plus 1, or tau was now 1 over omega sub c. This now says, oh, when omega is equal to omega sub c, we have 1 plus j for our factor, and the angle of that factor, I hope you can see that, is now a real part of 1, an imaginary part of 1, equal components of real and imaginary. That says that we have an angle of 45 degrees. So that now, for our pull factor being linear, the angle of that below frequencies less than 1/10 of the break frequency, we're at 0 degrees. A factor of 10 beyond the break frequency, we're downstairs, we're at minus 90 degrees. That's why this is now important. And in between, at the sweet spot, if this was now a pull factor, it would be a minus, I'm sorry, that raised to the minus 1. So now we are really just going to be down 45 degrees, so that we now are at minus 45 degrees, and we simply said, I'm drawing challenge, so I'm just wanting to do this with straight lines, and now I connect a straight line between the two extremes, the high extreme and the low extreme, and in fact in the middle I have a contribution of 45 degrees. And let me go ahead and clean this up for later. But in fact, now this is all there is to sketching the phase curve for a linear factor. And in this case, since it's downstairs, it's going down to minus 90 degrees. That's our pull factor's phase for a linear factor. It's a straight line, 0 degrees. We then have this slope of minus 45 degrees per decade. Here is 1 decade. And here is another decade, which means then that our angle transitions between its two extremes over a 2-decade interval. It turns on slope a decade before the break. It turns off its slope a decade above the break. And that's what makes the phase curves a little bit more challenging to draw than the magnitude curves. The magnitude curves, once they kick on, once they break, they continue to slope. The phase actually kicks in or breaks a decade before the break. Can that be any more confusing? And then it quits breaking or quits sloping a decade after the break. Here is the straight line approximation for the phase. The straight line approximation for the magnitude, again, goes flat until the break, and then it slopes at minus 20 degrees. The phase curve is flat until a decade before the break. It slopes just over a 2-decade region or interval in frequency, and then it stops sloping, and it leaves or stops or stays at minus 90 degrees. I hope that now helps our understanding of a Bode plot sketch of this particular structure or first order expression transfer function. And again, the time constant form, there's nothing magic about it. We can produce that k over tau s plus 1 for any kind of first order transfer function that you might be given. We simply factor out or normalize that constant coefficient to equal 1. That now puts it in time constant form, and we can identify the appropriate gain and the time constant tau for our particular situation. I hope that now helps understand why we can quickly sketch this magnitude behavior and this phase behavior for a linear first order factor.